You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. We will now take some time to learn about the link object. Links are massless and dragless connections between 2 other objects in a model. They are represented in the 3D view by a straight line between 2 points. There is no strong end A to end B convention like we have with lines. There are 2 types of link available, the tether and the spring damper. We'll come back to the spring damper type later. The tether link is a simple linear elastic tie that can take tension but not compression. This can be likened to the behaviour of an elastic band. The extent to which it will increase in length under load is governed by the stiffness, which acts only in the axial direction. If the distance between the 2 ends is less than the unstretched length defined on the data form, then the tension will equal 0. Links are a simple object and are useful for modelling short lines such as ropes or bridle lines, where mass and drag are likely to be insignificant. Where mass and/or drag could have an effect on the system response, it would be more appropriate to use a line instead of a link. We'll put together a simple example now which shows the difference in response between 2 payloads, one using a link and one using a line. The model requires 4 objects: a line, a link, and 2 3D buoys. Buoys will be covered in a later video, but they are being used here to represent the mass of the payload, one connected to the line and the other connected to the link. The 3D buoys will be identical, so it will be most efficient to create the first and then copy-paste it to create the second. The model will use the settings shown here in the table. First of all, we'll edit the environment settings to remove the waves by setting a wave height of 0 and to introduce a current of 2 meters per second. I'll choose a ramped current by checking this box, simply to allow us to see the change in the line response as the current is introduced during the build-up period. Next we'll set up the first 3D buoy. This allows us to introduce mass to represent some sort of payload. We'll position it at 0, 0, -10. The buoyancy of a buoy is automatically calculated based on its mass and volume. The volume will need to be reduced to ensure that this buoy is net heavy. A quick check of the properties report, accessed via the context menu, shows us that this is net buoyant with the default volume. The submerged mass is negative. Changing the volume to 1 cubic meter and looking at the properties report again shows us that that submerged mass is now a positive value, which means it is net heavy. As I mentioned previously, we will look at buoys in more detail in a later video. Note that the drag properties for the buoy are all 0. We want to avoid the buoys influencing the model response so that we can focus on the line and the link. Note also that the buoy connection is free. This makes it the parent object. The line and link will be connected to their respective buoys, making them the child objects. Before I copy this to create a second buoy, I will rename this one to make reference to the line, as this one will be for the payload using a line. Remember, to create a duplicate of an existing object, we just need to select it in the model browser and use the copy-paste options in the context menu, or use the keyboard shortcuts Ctrl-C and Ctrl-V. We now have a second buoy, which we can also rename to make reference to the link object. Moving on to the line, it is 20 meters long with 1 meter segmentation. End A is fixed at 0, 0, 10, and end B is connected to the line 3D buoy at 0, 0, 0. Finally, the link. End A is fixed at 0, 0, 10, and end B is connected to the link 3D buoy at 0, 0, 0. It has an unstretched length of 20 meters and a stiffness of 700 E3 kilonewtons, matching the axial stiffness of the line. We should be able to run the analysis now, but when we run statics, we experience a statics calculation failure. The statics progress window indicates it's because of an indeterminate case and references a singular Jacobian. OrcaFlex uses the Jacobian matrix, which is the rate of change of force with small changes in position, effectively the stiffness matrix, to decide which direction to move objects for the next iteration of the calculation. More specifically, a singular Jacobian happens when the solver is at a point where all directions it can go in its own internal space in which it hunts for the solution, are equally likely. It has no way of deciding where to take its next guess. In some cases, it may also mean that there are an infinite number of valid solutions. For instance, if you have a 3 degree of freedom vessel in statics on a flat sea, then the yaw could be any angle and it would still be a valid static solution. One of the ways we can overcome this issue is to reposition objects in the reset state such that the solver has a clearer idea of the direction it needs to move an object. The issue arises in this model with the link and its 3D buoy. The link has no mass properties. It is 20 meters long, and end A and end B are positioned exactly 20 meters apart. Consequently, at the very start of statics, it is difficult to identify the initial restoring force direction. We can help this by moving the link 3D buoy down slightly, such that the link is in tension at the start of statics, meaning the restoring force is immediately upwards. I'll move the buoy down by 0.1 meters. And run statics again. And we see that statics now solves immediately. Problem solved. If we move on to dynamics, we see the line move in response to the current, but the link stays still. Running a replay shows the line gradually move to the left as the current is ramped. The lesson in this example is simply to consider the drag and mass properties of the line you wish to model using a link. If they might be significant, a line would be a more appropriate object to use. We're going to move on now to create another example with which to compare a tether link to a spring damper link later on. It uses the data in this table. This model requires 3 objects: a vessel, a line, and a link. We'll set these objects up using the data in the table. The vessel is placed at the global origin. All other properties can be left at their default settings. The line stays at the default length of 100 meters, but with 2 meter segmentation. At end A, it is connected to the vessel at a position of 35, 0, and -7. And at end B, it remains fixed at a position of 85, 0, -20. The link remains fixed at end A at a position of 65, 0, -5, with end B connected to the line at an arc length of 32 meters. The tether link is quite a simple object. The only properties we need to set are the unstretched length, which is 35 meters, and the axial stiffness, which is left at the default value of 1000 kilonewtons. We can now run this model and watch the response as a replay is run. I've saved this file as tether.sim. Before we look at some results, it's interesting to note that we can hover over a link in the wireframe view, and the tooltip tells us the tension of the link in its current state. To help review the simulation in more detail, we will look at two link results, time histories for length and tension. On the result form, we'll select time history, the link object, and whole simulation. Now, because we know we need multiple results, we can hold the Control key while selecting the variables, tension and length. Then, when we press Show, we're presented with two separate time history graphs alongside the 3D view. My 3D view has now been relegated to the lower right corner of my monitor. I'd like to make this the main view, with the two results windows on the right and both of them being the same size. To do this, I select the 3D view, go to the Window menu, and select Tile Vertical. This places the selected view at the top left. Alternatively, Tile Horizontal will place the view at the top left but running horizontally across the screen rather than vertically down. We can save a combination of 3D views and results for future use by using a workspace file. This is important to do at this stage because I'd like to make a change to this model and come back to the same results later. Once you have a workspace ready, in the Workspace menu, select Save and give it a name. This can be any name, and you can save multiple workspaces for one file. Remember that a tether link is a simple linear elastic tie that can take tension but not compression. If the distance between the two ends is less than the unstretched length defined on the data form, then the tension will equal 0. The unstretched length, as defined on the link data form, is 35 meters. As the vessel responds to the passing waves, we see the tension rise and fall. Note the point where it falls to 0. Looking to the link length result, this is the point at which the link length drops below 35 meters, the unstretched length. So, this confirms the ability of a link to experience tension, but not compression. We will now convert the model to use a spring damper link and look at the same results to see what has changed. Note that when the model has been reset, the results windows stay open. We can choose to leave these here, or optionally close them and open the previously saved workspace file when we need the results again. The spring damper link can take both tension and compression, and both the spring and damper components can be non-linear, using data tables for length versus tension for stiffness, and velocity versus tension for damping. For this comparison case, we will use a linear stiffness value. The unstretched length is still 35 meters, as with the tether link. However, there is a subtle difference with the units for the stiffness. For the tether link, the stiffness is a force in kilonewtons. For the spring damper link, the stiffness is a force per unit length, kilonewtons per meter by default. In order to compare the two models, we need to calculate the stiffness as a force per unit length, which is equivalent to the stiffness divided by the unstretched length, which is 1000 divided by 35, which equals 28.571 kilonewtons per meter. You can see the two formulae for the links if you highlight the stiffness value and press F1. This opens up the documentation at the relevant section. Finally, we will leave the damping at the default setting of 0. We'll run Dynamics again and save this as a new simulation file with the file name springdamper.sim. As I mentioned, we can review the same results as with the TetherLink model by opening the workspace file we saved earlier. Go to the workspace menu and select the appropriate WRK file from the list. The only difference we see between these two link types is that when the unstretched length of the spring damper link falls below 35, the link tension goes negative. In other words, it is now able to take compression. Before we finish this video, I'll just show you a few examples of the use of links in some of our published examples. These are all available for download from the examples area of our website. Firstly, in example A01 Pliant Wave Riser, tether links are used to tether the riser to the seabed in the touchdown region to control the response of the riser at touchdown. In example F06 Spool Piece Maneuvering, tether links are used to model the slings supporting this spool piece. The slings are likely to remain in tension throughout, so tether links would be a suitable type to use. Finally, in example F02 Passive Compensation, these payload bridle lines once again utilize tether links. And that concludes this video about the link object. We will move on to winches in the next video.